Good morning, dear students, and once again, welcome back to our course. In the last lecture, we discussed in detail about the concept of signal flow graph and the importance of Mason's gain formula that plays an important role in order to obtain the transfer function of a system if the signal flow graph is known to us. And then we solve some numerical on Mason's gain formula. From today's lecture, we are going to start one of the most important topic on control system that deal with the concept of block diagram. Now, what exactly block diagram is and how block diagram plays an important role to study the behavior of a system that we are going to cover through the coming 4 to 5 lectures of this particular course. So, our objective is that suppose we have the representation of a system in the form of block diagram. So first, our objective is how to represent a system in the form of block diagram, what exactly block diagram is, and then what informations we can indicate regarding the system through block diagram that we are going to cover. And then if we have the block diagram representation of a system, how to find its corresponding transfer function. That is again very important. For example, if we know the block diagram for a system, then how we can apply various rules related to block diagram reduction technique to convert that representation into its corresponding transfer function. That is our final objective. And based on this topic, you may have various types of numerical that are commonly asked in GATE exam, maybe for electrical domain, maybe for electronics and communication engineering student. That means the block diagram for a specific system is given to us, and our objective is to find out or convert that system into a single block, and whatever the gain available inside that block that indicate its parametric function, that means that indicate its corresponding transfer function. So how to apply various rules of block diagram reduction technique to convert into its equivalent parametric function, which is also called as transfer function, that we are going to learn in the coming sessions. So first, let us try to discuss what exactly block diagram is and how through this technique we are in a position to represent the behavior of a system. So block diagram is a graphical technique to represent the behavior of a system through various operating blocks. These are very important. That means it is a graphical technique through which we are trying to represent the behavior of a system through various operating blocks. Now, these blocks are so arranged that they will explain or replicate. This is very important. They will explain or replicate the exact relationship between the input and the output of the system. That means through those blocks, we are trying to explain, we are trying to define the relationship between the input and the output of that particular system. So that type of graphical representations where we are trying to represent the system through various operating blocks, and through those operating blocks we are trying to define the relationship between the input and the output of the system. That type of representation is called as block diagram representation. Now sometimes these blocks are also known as functional blocks. Now why they are called as functional blocks? Because inside those blocks we are trying to define the functionality of the system. For example, in some cases if the input is related to output by additive or by subtractive or by multiply with some constant parameter. So whatever the functionality through which the input and output are correlated with respect to each other, that functions we are trying to define inside that block. That's why sometimes those blocks are also called as functional block. And each block will represent some set of mathematical operation. As I told you, that it may possible that inside the block we need to uh, represent some kind of functions that may be additive, then subtractive, multiplier, division, or it may possible that inside that block we need to take simply a constant parameter just to provide the relationship between the input and the output. But the overall agenda is that in block diagram technique, we are trying to define the behavior of the system through set of blocks. And inside that block, we need to add some function. That function provide the relationship between the input and the output of the system. That is important. Now let us take an example. Suppose we have a physical system in the form shown over here, where we have inductor and resistor of value L and R respectively, and they are connected in series configuration. And to this particular combination we passed some current in the form of input, which is nothing but I of t, and based on this we have some voltage that is going to be induced across this particular pair, or we are going to experience a voltage drop, which is nothing but plus minus E of t. So in this case, this I of t is going to behave like an input to the system, and this E of t is going to be the output of the system. And here this L in series combination with R is going to be our system. Now our objective is to convert or represent this particular system into its corresponding block diagram. So how we can do that? Now in the previous case we learn, suppose we have the representation of system in the form of signal flow graph, we can convert that into its corresponding transfer function by applying the concept of Mason's gain formula. In the same way, suppose we have the system maybe in the form of some physical form, maybe in the form of some mathematical equations, then we learn how to obtain its corresponding signal flow graph. In the same way, suppose in this case we have the representation of system in physical form, where we know that in the system we have two elements. First one is inductor, second one is resistor, and both are connected in series configuration. And to that series configuration we have applied input in the form of current, and we are going to get output in the form of voltage. So how to convert this into its equivalent block diagram? So first we need to obtain its mathematical modeling. And once we know the mathematical modeling of this particular system, then we are going to find out what will be the relationship between this input with respect to the output, and that function we are going to place inside a block. That's why the block is called as functional block, because that block is going to define how input is related with the output, what will be the function. So that technique we need to implement over here in order to convert this representation of a system in physical form to its equivalent block diagram. So first we need to apply some logic to find out its mathematical modeling, maybe in say time domain, maybe in say frequency domain. But normally block diagram reduction technique or block diagram technique is applicable, or we want to apply this type of technique to the frequency domain representation of a system, because ultimately our objective is to find its transfer function, and transfer function is nothing but Laplace of output by Laplace of input. That means we are trying to represent the relationship between output and input in frequency domain. So whatever the mathematical modeling which we are going to get for this particular system, we will try to get in terms of frequency. That is important. So if you apply that logic, first of all what we are going to do, we will convert the frequency domain representation of a system into its equivalent block diagram. So how to convert this into its equivalent block diagram? So first we need to obtain its mathematical modeling, maybe in say time domain, maybe in say frequency domain. But normally block diagram reduction technique or block diagram technique is applicable, or we want to apply this type of technique to the given system into its equivalent frequency domain. And this is possible by applying the concept of what? Laplace transform. So here we know, you should know the basic fundamental conversions of RLC circuits if they are available in time domain, how we can represent them in frequency domain. For example, if we have the elements in time domain like capital R, then its equivalent representation in frequency domain will remain R, because R is nothing but frequency independent component. So the value of R in time will remain the same R in frequency. But in case of inductor, if it is available in time domain, we can represent that in frequency like S into L. In the same way, if we have capacitor, this we can represent as 1 upon S into C. So these conversions you have to remember, that in time domain, if we have RLC, in frequency they are going to be like R, SL, or 1 upon SC. Once you have done with this, now apply that logic to convert the system which is available to us in time into its equivalent representation in frequency. So instead of writing small I of t, we are going to replace them by capital I of s. In the same way, we have small e of t that we are going to represent by capital E of s. Now instead of writing L, we need to represent that by SL, and R will remain as it is. So this represent frequency domain or frequency domain representation for that particular system. Now in this case, this I of s is nothing but the input, this E of s is going to be the output, and this SL in combination with R indicate the system behavior. That is important. Now we need to apply the concept of network theorem in order to represent the relationship between input and output. Now from this equation it is very clear that output is nothing but input multiplied by the effective impedance of the system. Now here we have a combination of inductor and resistor, both are connected in series, so the effective impedance is going to be like R plus SL. So if you apply that logic, we can write the relationship between output and input like output E of S is going to be effective impedance of the system multiplied by the input. So V is nothing but I into R. So here V is nothing but E of S equals to I is nothing but I of S into R. Now instead of R, here we need to take equivalent impedance. So this is going to be equivalent impedance of the circuit, which is nothing but R plus SL or SL plus R. Now we know that this E of S is nothing but the output, and this I of S is nothing but the input. So here whatever the term which provide the relationship between output and input, this is going to be our parametric function. So SL plus R is nothing but our parametric function. That is important. And this parametric function is nothing but our transfer function. So if you want to represent this equation in terms of block, so how we are going to do that? So here we need to take a block. To this block we need to apply some input. So in this case the input is nothing but I of s, and output is going to be E of s, and the factor that define the relationship between input and output is nothing but SL plus R. This is the representation of this particular system in block diagram. I hope this point is clear to everyone. So this IS, if you apply input or excitation to a block of gain, or you can say parametric function of SL plus R, it is going to generate some output which is nothing but E of S, and this E of S is nothing but input times the gain. So input is nothing but I of S multiplied by gain will be your SL plus R. That is important. So above figure represent the block diagram of series RL circuit. So in this way, we are in a position to represent the given system into its equivalent block diagram. I hope this point is clear to everyone, because this is very important and this is very fundamental logic, that how we can represent a system if it is available in the form of physical form into its equivalent block diagram. The thing is that we first need to find its mathematical modeling, and then we need to club, or we need to identify the function that provides the relationship between output and input, and then we need to represent that function inside the block, providing input to the block and we are getting output from the block. That's it. So I want everyone to please note down this, because this is a very basic concept of block diagram. Now once, if you are done with this, then let us try to discuss some common terminologies which are normally used in block diagram, the way we discussed in case of signal flow graph, like what is node, what is input node, what is output node, what is intermediate node, what is the concept of forward path, then forward path gain, loop, loop gain, pair of non-touching loop, two non-touching loop, three non-touching loop, and so on. In the same way, there are some terms which are commonly used in block diagram. For example, what is summing point, what is takeoff point, that what is the forward path concept, what is the feedback path concept, what is forward path element. That terms we first discussed in this section, and then we are going to discuss how to find the transfer function for a closed loop control system. So first point is nothing but output. What do you mean by output? And the thing is that you have to note down all these points one by one. So output is nothing but the response of the system, or it is nothing but the response generated by the block when it is excited by some input excitation. So whatever the response generated by the block when it is provided by some set of input, that response is nothing but output. For example, in our previous case, this E of S indicate the output. That is important. So here this E of S is going to be the output, or you can say exciting a response, not excitation, because excitation is input. So it is going to be response. So E of S indicate the output. Now what is input? Input is nothing but the excitation that we applied to a block in order to generate the desired output. So whatever the input that we have applied in the form of excitation to a system, so that it will generate some desired output, that input or that excitation is known as input. For example, with respect to this particular case, this I of S is going to be the input. So this is going to be the input, or you can say excitation. So in control system, output is known as response, input is known as excitation. That you have to remember. So here I of S indicate the input. So I want everyone to please note down this point, what exactly output is, what exactly input is. So once we have done with this, what exactly output is, what exactly input is, now let us try to understand what exactly the gain of block or block gain. So what is block gain? So it is simply a mathematical function or a parametric function that presents inside the block, that is called as block gain. So whatever the value which we are going to mention inside the block, that entire value indicate the gain of that particular block. For example, in block diagram we have various sets of block, and inside the block if we write say capital R, so this capital R indicate the gain of this particular block. Now instead of writing capital R, if in the block I can write here as R plus SL, so this R plus SL indicate the gain of this particular block. Or I can write here as S divided by 4 plus 2S. So this S divided by 4 plus 2S indicate the gain of this particular block. So whatever the mathematical function that we have mentioned inside the block, that represent its gain. That's it. So with respect to our previous case, SL plus R indicate the gain of the block. So SL plus R indicate the gain of the block. That is important. Now what will be the relationship between this output, input and gain of the block? So the thumb rule is very simple that you have to remember, and the rule is that suppose we have a block of gain say A, to this we applied some input in the form of X and we are trying to get output in the form of Y. So what is the relationship between this output, input and gain? So output is always going to be equals to input multiplied by the gain of the system. That is important. So in this case output is Y, input is going to be X and gain is going to be A. So this is the fundamental mathematical relationship between output, gain and input. This is applicable for any block. Output is always going to be input times the gain. That you have to remember. The same thing is mentioned over here. See, output is always going to be input times the gain. Now in this case, output is nothing but E of S. Gain is nothing but SL plus R, because I told you that what is gain? Whatever the thing, whatever the mathematical function or the parametric function that we have mentioned inside the block that represent the gain of that particular block. So here SL plus R indicate the gain into input of the block. So input is I of S. So output is input times the gain, or you can say output is gain times the input. Both are the same thing. The thing is that if you have to calculate output, if you know the input, if you know the gain of the block, multiply input to gain, you will get output, which is nothing but the response of the system. Now let us try to discuss what exactly summing point is. Summing point plays a very important role in block diagram representation of a system. So let us try to discuss what exactly summing point is. Now summing point is a point in block diagram where two or more than two signals are added or subtracted. So it is nothing but a point which is commonly mentioned in the block diagram representation technique to add or to subtract two or more than two signals at a time. So that is nothing but a summing point. Now, for example, in this figure, this circle with some input signals having some finite signs mentioned at their corresponding arrowhead like plus, plus and minus. So this particular symbol or this particular point is known as summing point. Now at this particular summing point we have some input signals and we are trying to find what will be the output of this summing point. So here we have three input signal. First one is R of S with plus sign, second one is R2 of S with again plus sign, and third one is R3 of S with negative sign. So here we have three input signal, and out of these three input signal, two are positive and one will be negative. So we are trying to find output, which is nothing but response. So it is going to be like C of S is input R of S with its sign. So here sign is plus. So I need to write here as plus. And then second input is R2 of S with sign plus. So it is going to be like plus R2 of S. And then third signal is R3 of S with sign minus. So here we need to take minus R3 of S. So in this way, we are trying to find out the output corresponding to various types of input signals which are available at the summing point. So R1 of S plus R2 of S minus R3 of S is going to be DC of S. So I hope this point is clear to everyone what is gain of the block and what will be the relationship between output gain and the input and what is the meaning of summing point. So summing point is a point available in the block diagram that is basically used to add or subtract two or more than two signals at a time. So please note down these points because these are fundamental points that plays an important role if we are solving numerical on block diagram reduction technique. That type of numericals are commonly asked in gate. The thing is that you have the representation of signal in the form of block diagram and your objective is to find its corresponding transfer function using BDRT, block diagram reduction technique rule. If you are done with this, let us move ahead. Now what is takeoff point? Takeoff point is a point in block diagram where the signals are taken for a feedback purpose. So just like we have a summing point in block diagram where we are trying to add or subtract two or more than two signal at a time, in the same way, on the same topology, we are having one more point in the block diagram that is called as takeoff point. Now what exactly takeoff point is? It is nothing but a point in a block diagram where we are going to take the signals for feedback purpose. That is important. That may be a positive feedback or that may be a negative feedback. So for example, अगर आपको कोई एक सिग्नल लेना है फीडबैक पर्पस के लिए तो जिस पॉइंट से आप वो सिग्नल को ले रहे हो दैट पॉइंट इज कॉल्ड एज द टेक ऑफ पॉइंट. For example, if you see this structure, so here we have a block and inside that block we have mentioned some parametric function which is nothing but SL plus R. To this we provide some input in the form of I of S and we are getting output in the form of E of S. Now suppose we want to take this output for feedback purpose. So this point is known as take off point. Take off point. Why it is called as takeoff point? Because at this particular point we are trying to take this signal. Now what is the value of this signal? This signal is nothing but the output, which is nothing but E of S. So this E of S we have taken for feedback purpose. So here the feedback signal we have represented by sign B of S. Now in this case the value of this B of S is going to be equals to what? E of S, because E of S is the signal that we have taken for feedback purpose. Now because that signal is feedback, that's why we have indicated that by signal or symbol B of S. But in this case B of S is going to be E of S. So this is nothing but takeoff point. I hope this point is clear to everyone what exactly takeoff point is. Now this signal may be positive or it may be negative. For example, if we have taken the signal in the positive sense, it is called as positive feedback. Suppose we have taken the signal in the negative sense, then it is called as negative feedback. Now let us try to discuss what exactly forward path is. The way we define forward path in case of signal flow graph, in the same way we can define this for block diagram. Again the topology will remain the same. What is forward path? When the signal is going to flow from input towards the output, the path is known as forward path. See, the same definition is mentioned over here. It is a path where the signal is always going to flow from input to the output. That is important. So with respect to this particular block diagram, if we want to define what exactly forward path is, so here this indicate the input and this indicate the output. And suppose if we are moving from input to the output, so this path is known as forward path. So this is indicated over here. G1 of S, G2 of S, G3 of S indicate the forward path. I hope this point is clear to everyone, what exactly the takeoff point is and what exactly the forward path is. So I want you to please note down these points, because these points are very important if you really want to understand what exactly block diagram reduction technique is. If you have done with this, now let us move ahead and let us try to understand some more topologies which are used in block diagram. Now, what is the meaning of feedback path? The way we define forward path, where forward path is nothing but a path where signal is always moves from input to output. In the same way, we have reverse topology, and that reverse topology is nothing but feedback path, when the signal is going to move from output to input. Then that type of path is called as feedback path. So to understand this, let us try to see this figure. Now here we have represented a general closed loop control system where this G of S indicate the gain. Now this is also known as gain of forward path. Now why it is called as gain of forward path? Because this gain G of S is connected in such a way that the flow of signal through this gain is from input to output. That's why G of S is called as forward path gain. Now what is feedback path? When the flow of signal is from output to input like this, then it is called as a feedback path. And whatever the gain available in the feedback path, that is called as feedback path gain. Now here H of S indicate your feedback path gain. That is important. And whatever the signal which is flowing through this feedback path, this is called as feedback signal. Feedback signal, that is important. Now I told you that feedback signal may be positive or it may be negative. Hence we are having two different types of topology for feedback. It may be a positive feedback or it may be a negative feedback. And normally in control system we prefer negative feedback system to analyze the behavior of system, because in this case the systems are more stable as compared to positive feedback system. So what is feedback path? When the flow of signal is from output to input, then it is called as feedback path. So B of S is called as feedback element, H of S is called as gain of feedback path, G of S is called as gain of forward path. That is important. So this path is called as feedback path. I hope this point is clear to everyone. I want everyone to draw this structure and note down what is the meaning of this feedback path. If you have done with this, now the same thing is mentioned over here. G of S is forward path gain, H of S is called as feedback path gain. So this is what the concept of feedback path. The thing is that in this case, signal is going to move from output to the input. Now let us try to do the analysis, or let us try to find out the transfer function for a simple closed loop system. For example, if you have the representation of system through this block diagram, now this is nothing but your block diagram, and if you are interested to represent this particular block diagram into a simple block like this, where the input to the system is nothing but R of S, the output of the system is going to be C of S, and the block is going to be like this. And what is the gain available over here? That is nothing but its transfer function. So how to find the value of this TF, transfer function of the system? Now in this case, in order to find the relationship between output and input, we need to apply some fundamental logics that we have learned so far in this particular course. Now here, this E of S is nothing but the error signal, R of S is the reference input, B of S indicate the feedback signal, and here the nature of feedback signal we have taken as negative. That is important. That means we have considered a negative feedback control system. That's why we have taken the error as minus sign. G of S indicate the gain of forward path, H of S indicate the gain of feedback path, and C of S indicate the controlled output or the response. That is important. Now our objective is to find the transfer function of this system. So transfer function of the system is going to be like output by input. As I told you, that transfer function nothing but what? It is the ratio of Laplace of output by Laplace of input. So T by F is going to be like C of S by R of S. So this we need to find out. So how to find this? Now in this case we need to apply simple mathematical operating equations. So first, mathematically we can write the relationship between this C of S with respect to this E of S. Now if you focus on this particular portion, this block represent a gain of value G of S. So to with respect to this block, the input is E of S, which is the error signal, and output is going to be C of S, which is the actual output of the system. So if you want to define the relationship between this output, gain, and input, so it is going to be like output equals to input times the gain. See, output is equals to input times the gain. Let this will be equation number 1. I hope this is clear to everyone, and everyone must write these equations one by one, because this is the very important concepts where we are trying to define. Suppose we have the representation of a system, a closed loop system, how to find its corresponding transfer function. So this will be equation number 1. In the same way, at summing point, let us try to find out what will be the relationship between output and input signal. So with respect to this summing point, output is error signal, which is nothing but E of S, and we have two input. First one is R of S and second one is B of S. And that too, we have considered that the nature of feedback signal is negative. So I can write here as output E of S is nothing but R of S minus B of S. That this will be equation number 2. Now, suppose we want to find the relationship between this B of S with respect to the input. Now, if you focus on this feedback path, here the input to the block is nothing but C of S, and the output of the block is nothing but B of S, and the gain of the block is H of S. So again we can apply the same topology, like output is nothing but input times the gain. So see, output D of S is going to be input times the gain. That this will be your equation number 3. Now what we are going to do, we are going to club equation 2 and 3. So in equation number 2, this B of S we are going to represent by C of S into H of S. If you do that, we can write here as error signal E of S is going to be equals to R of S minus B of S, but B of S is nothing but C of S into H of S. Now, what we are going to do, we are going to club this equation number 1 and equation number 4. So in equation number 1, we have the relationship between output with respect to gain and the input, which is nothing but error signal. Now this error signal we are going to revision by this entire term, which is R of s in bracket C of s into H of s. So if you combine equation 1 and 3, we can write this equation. Now we need to reshuffle, we need to club, take common pot on same side, and ultimately we need to find the relationship between output by input, that too in the form of ratio. So if you solve this equation one by one, step by step, you will get this as an output. So here C of s by R of s is going to be G of s whole divided by 1 plus G of s into H of s. So I'm writing this equation over here. C of s by R of s is going to be G of s whole divided by 1 plus G of s into H of s. This indicates the transfer function of a general closed loop control system where G of s indicate forward path gain, H of s indicate feedback path gain. And why we have taken here plus sign, because it is, we are getting that sign if you solve those equations. So you have to remember this, because we have taken a negative feedback system, negative feedback system, that's why we are getting plus sign in the denominator polynomial function of the transfer function, 1 plus. The same system you can solve through or by taking positive feedback system. For positive, you will get negative sign in the denominator polynomial function of the transfer function. So this formula you have to remember. Like C of s by R of s is going to be G of s upon 1 plus G of s into H of s. So please write down this as a final answer. So same thing is mentioned over here. Now suppose we want to represent the system through a single block. So instead of drawing the entire system, now we need to take only one block, and inside that block we need to provide the relationship between output and input, and that is going to be G of s whole divided by 1 plus G of s into H of s. So above figure indicate the reduced block diagram representation for the given system. So कहने का मतलब है कि जो आपके पास सिस्टम अवेलेबल था, which one, the bigger one, where we have the gain like G of s, then somewhere here we have the summing point, and then here we have R of s, and the output is C of s. Then we are having a feedback gain H of s like this. So no need to draw this structure, simply draw this single block having a gain equals to G of s upon 1 plus G of s into H of s. This we have reduced to a single block, and this G of s upon 1 plus G of s into H of s indicate its transfer function. In the same way, as I told you that instead of taking negative feedback signal, suppose if you take positive feedback signal, then what will happen? Now see here, instead of taking negative feedback, if you take positive feedback signal, and if you apply the same logic, you will get this as an output. So you have to remember this. There is a fine difference between negative and positive feedback signal. If the system is negative, you will get positive in the denominator. If you have positive feedback signal, you will get negative in the denominator polynomial function. This you have to remember. So in general, we can write this as C of S divided by R of S is going to be like G of S whole divided by 1 plus minus G of S into H of S, plus for negative feedback and minus for positive feedback. This is very important. So the same thing is mentioned over here. Now this indicate general representation of a closed loop control system where we have controller and plant. As we have discussed what exactly plant is the portion of a system whose function is to be controlled. And what is controller is the element uh, through which we are going to control the function of the plant. So here G of S indicate forward path gain, H of S indicate feedback path gain, E of S indicate the error signal. Then somewhere over here we must have B of S, where B of S indicate feedback signal, R of S the reference input, C of S is the control output, and here we have taken both possibility, positive feedback signal as well as negative feedback signal. So if you apply block diagram reduction technique, we can write them like R of S provided as an input to a block of gain C of G of S upon 1 plus minus G of S into H of S. Now see, if you take negative feedback, you will get plus. If you take positive feedback, you will get minus. This you have to remember. So I want everyone to please note down these points. These are very fundamental mathematical set of equations that we are going to apply many times in the coming lectures of control system. G of S upon 1 plus minus G of S into H of S. For negative feedback system, we need to take plus sign. For positive feedback system, we need to take minus sign. If you have done with this, now let us try to start the next very important topic in case of block diagram section that deals with different types of rule related to block diagram reduction technique. Now this is what the actual topic where we need to focus, and based on this topic we are having various numericals that are commonly asked in gate exam. Now in this section our objective is to understand what are the different types of rule which are normally used for block diagram reduction technique. For example, if you have the representation of a system in the form of block diagram, and suppose if you want to find its transfer function, that means if you want to convert that into a single equivalent block, then whatever the gain available inside that block, that gain indicate its corresponding transfer function. So how to convert a complicated block diagram into its corresponding equivalent single block diagram, that we can do by applying various rules associated with block diagram reduction technique. So we are going to learn some 7 to 8 different types of rule, and what is the significance of each rule. For example, if you have two or more than two blocks connected in series, how to club them into an equivalent single block. In the same way, suppose if you have two or more than two blocks connected in parallel, how to identify that whether they are connected in parallel, and suppose they are connected in parallel, how to club them into an equivalent single block. In the same way, how to apply elimination of feedback path. Then what will happen if you shift the takeoff point after a block? What will happen if you shift a takeoff point before a block? In the same way, what will happen if you shift a summing point after a block or before a block? That all rules we are going to discuss in this particular topic. So first rule is blocks when they are connected in series connection. Suppose if we have two or more than two blocks, and if they are connected in series, how to find their equivalent block diagram, or how to represent them by a single block. So this is what the figure is, where we have three block, like G1 of S, G2 of S, and G3 of S. So here G1 of S indicate first block, G2 of S indicate second block, and G3 of S indicate the third block. And suppose we want to represent them by a single block. So how to represent them? Again, what we need to do, we need to find the output in the intermediate stages, and then we need to club that output with respect to the main input, and whatever the parametric function that define the relationship between output and the input, that parametric function we need to place inside a single block. That's it. So here blocks are said to be in series connection when they are connected back to back. This is very important, and they do not have any summing point or takeoff point in between them. So how to identify that whether the blocks are connected in series or not? The thing is that when they are connected back to back and they do not have any summing point or takeoff point, in between them. So when we have the representation of blocks in this particular fashion, then it is said to be the blocks connected in series configuration. Now how to find their equivalent gain? So the equivalent gain is like, we need to find the output in the intermediate stages. For example, the output of first block is going to be like input multiplied by gain. So here input is R of S and gain of the first block is G1 of S. Now with respect to block 2, what will be the input? This will be the input. And what will be the output? Again the same topology. Output is nothing but input multiplied by gain. So input is R of S into G1 of S multiplied by gain. So this is going to be G2 of S. Now this will be the input for block number 3, and the output of block number 3 is nothing but the output of the system. So the C of S is going to be like input multiplied by gain. So input is going to be like R of S into G1 of S into G2 of S multiplied by G3 of S. So this is going to be C of S. So here this indicate the input, this indicate the output. So whatever the parametric function that should define the relationship between output input is known as the system transfer function or parametric function of the system. So here we can define this as output is nothing but input times the gain, and in this case the gain is G1 of S, then G2 of S, and then G3 of S, like this. This is very important. So what is the conclusion? Finally we conclude that output is nothing but input times the gain. That means when the blocks are connected in series configuration, the equivalent gain is nothing but the multiplication of individual block gain. That is very important. That means when the blocks are connected in series configuration, the output, or you can say the overall output of the system, is simply the product of gain of individual block. That means if we have two or more than two blocks and when they are connected in series configuration, the equivalent gain is supposed to be the product of gain of individual block. This is very important. This is what final Answer is, so this you have to remember that when we have blocks and they are connected in series configuration or combination, the resultant gain is simply the product of individual block gain. This is very important. So whenever we have two or more than two blocks connected in series configuration, the output is going to be the product of individual block gain. So today we will stop at this particular point. In the next lecture, we will continue with different rules that plays an important role for block diagram reduction technique. Thank you.